Good day, everyone. Reporting from Team BB Girls are Danelle BERNIDO, Juremae Pesidas, and Loren TORRECAMPO. And we are to discuss a probability problem with its solution. Suppose this is the situation. You arrive at the bus stop at 10 o'clock, knowing that the bus will arrive at some time uniformly distributed between 10 and 10:30. We are going to answer the following questions. A. What is the probability that you will have to wait longer than 10 minutes? B. If at 10:15 the bus has not arrived yet, what is the probability that you will have to wait at least an additional 10 minutes? Note the given that the bus arrives uniformly at the bus stop between 10 a.m. and 10:30 a.m. Let X denote the arrival of the bus at the bus stop in minutes. That is 10x. Since the total of all the probabilities in a sample space is 1, and there are 30 minutes between the time interval 10 a.m. and 10:30 a.m., then x is a uniform random variable having the density function f of x is equal to 1 over 30, where x is between the closed interval 0 and 30, and 0 elsewhere.
For the first question, to compute for the probability that you will have to wait longer than 10 minutes, we will have the notation p of x greater than 10. That is equal to the definite integral of f of x dx between 10 and 30. Because arriving at 10 a.m. and waiting at least 10 minutes means that the bus may arrive between approximately 10:01 and 10:30. Substituting 1 over 30 to f of x, we now have the definite integral of 1 over 30 dx between 10 and 30. Evaluating the integral, we have 1 over 30x evaluated at x equals 10 and x equals 30. Using our prior knowledge in integration, the equation results to 2/3. Therefore, the probability that the passenger arriving at 10 a.m. at the bus stop will have to wait at least 10 minutes is 2/3. For the second question, to compute for the probability that you will have to wait at least an additional 10 minutes if the bus has still not yet arrived at 10:15 a.m., we will have the notation p of x greater than 25, given that x is greater than 15. Observe that this is a conditional probability. Thus, the expression will be evaluated as the probability of the intersection of x greater than 25 and x greater than 15 divided by the probability of x greater than 15. The intersection of x greater than 25 and x greater than 15, as you see in the illustration, is x greater than 25. So the equation will reduce to the probability of x greater than 25 over probability of x greater than 15. This will further equal to the definite integral of 1 over 30 dx from 25 to 30 over definite integral of 1 over 30 dx from 15 to 30. Again, using our prior knowledge of integration, we arrive at 1/3. Hence, the probability that you will have to wait at least an additional 10 minutes if the bus has still not yet arrived at 10:15 a.m. is 1/3.
Another way to look at the situation is to treat the probability as an area of a rectangle representing the uniform probability distribution with an area of 1. Given a total area of 1, we divide it by the total units inside the interval, which in this case is 30, and we obtain the height, which is always 1 over 30 in the interval of interest. The width is the slice or the part of the distribution specifically mentioned in each question, defined by b minus a, where b is the bigger number and a is the smaller number. For the first question, our width is from 10 to 30. That is, 30 minus 10 equals 20. So, 1 over 30 multiplied by 20, that is 2/3. We arrived at the same solution. For the second question, we will consider two rectangle areas and divide them. For our numerator, our width from 25 to 30 is 5. So, 1 over 30 multiplied by 5, that is 1 over 6. For the denominator, our width from 15 to 30 is 15. So, 1 over 30 multiplied by 15, that is 1/2. Finally, 1 over 6 divided by 1/2 equals to 1/3. Hence, both approaches lead to the same answers. To conclude this report, we will give you a glimpse of the probability distribution behind the solution. The random variable x that we have mentioned earlier is specifically called a uniform random variable because of course it has a uniform probability distribution. By definition, if a is lesser than b, then a random variable x is said to have a continuous uniform probability distribution on the open interval ab if and only if the density function of x is defined by f of x equals 1 over b minus a in the closed interval ab and 0 elsewhere.